Good day, students. This is topic 1, lesson 3, reasoning and proofs. In this lesson, we're going to be looking at several things. We're going to be looking at proofs in regards to two-column proofs, flow proofs, and paragraph proofs, and get into how we develop a proof based on certain types of reasoning. And then we're going to use those proofs to create algebraic proofs based on lines and angles and the postulates and theorems that we've learned in the previous lessons. Okay, so let's look at example 1. It says circle which type of reasoning is being used in each of the following situations. State how you know. So the first one says it has rained the past 3 days. Jaquan makes a conjecture that it will rain again tomorrow. So let's think about this. Inductive reasoning means that I'm looking at a pattern, something that happens over and over and over again, and then from that pattern I can state a conclusion or hypothesis of something that will happen next. Deductive reasoning looks at and observes a situation, makes a hypothesis, and then predicts, and we can then verify that it's going to happen for every situation. So inductive reasoning, we can look at a pattern, but it may not necessarily always be true. And deductive reasoning means that I can prove for sure and verify that it will happen every single time. So which one would be the best possibility for this first example? Well, if I know it rained yesterday and the day before that, and it's raining today, so that's 3 days of rain right there, then I can possibly say that the next day is going to rain again. That would be called inductive reasoning. We see the pattern from the past 3 days, so we can make a prediction that possibly it will rain tomorrow. The second one says Maria is writing a list of numbers. She asks Suzanne what the next number would be. After looking at the list 7, 14, 21, 28, 35, 42, Suzanne states the next number will be 49. Well, again, we can look at this sequence of numbers and see if we see a pattern that takes place. So let's look at what we have in between each one. So I see the pattern. Do you see the pattern? Between 7 and 14, I have plus 7. Between 14 and 21, I have plus 7. 21 to 28 is plus 7. 28 to 35 is plus 7. 35 to 42 is plus 7. And if we use this pattern that we had from the previous numbers, if I add 7 to 42, guess what am I going to get? I'm going to get 49. So that means Susan's hypothesis, based on her pattern or observing the pattern, was correct, that the next number would be 49. So we can call this inductive reasoning as well, based on her pattern. The next one says Kai adds the sides of an equilateral triangle and finds the length of the perimeter to be 3 times the length of one side. He guesses that the perimeter of every equilateral triangle will be 3 times the length of a side. So let's use a picture to demonstrate Kai's findings. So we know an equilateral triangle means that all sides of that triangle are equal, or what we call congruent in geometry, and we use these little markings here to determine that they are congruent. All right, so it says here that the perimeter of an equilateral triangle will have the length to be 3 times the length of the perimeter. 3 times the length of each side will equal the perimeter. So let's put some numbers to this. Say if I said that the length of this equilateral triangle was 3 here, 3 here, and 3 here. So that means that the perimeter would equal 3 times the length, which would be 3 of the sides. So that perimeter would be 9, right? And 9 is 3 times bigger than 3, which is the length of the side. But let's see if I can use a different number. Let's say I use 4. So say I change this now to 4. Okay, I changed the size to 4. Let's see if that actually happens or works also for the side lengths being 4. So 3 times the length, that would be 3 times 4. And 3 times 4 we know is 12. Well, is 12 3 times more than 4? Well, yes, it is. So that means that my observation and hypothesis that I made by making my my formula here, that means my formula is working for every situation. So that means I can verify that every equilateral triangle's side lengths, I can say that the perimeter is going to be 3 times those side lengths. So what can we conclude in this situation? We can conclude that this is deductive reasoning because I was able to come up with a formula to prove and verify that this is actually true. Okay, so we have example 2, which states, provide a counterexample to show that the statement is false. You may use words or draw a diagram. So here the word counterexample you should remember from your warm-up activity. In that warm-up activity, you saw this vocabulary word counterexample, which pretty much means if you can find a statement that is counter or opposite to what is being stated originally, or if you can show a picture or drawing that is opposite or false to the statement or picture that's originally given, then that is what we call a counterexample. So let's look at the statement that we have here. If segment AB, and this little symbol right here represents congruent, we have our little geometry notation cheat sheet at the bottom here, congruent. If segment AB is congruent to segment BC, that means pretty much those two segments are the same, equal, then B is the midpoint of BC. Well, let's first draw an example of the two segments. So they gave us two segments. The first one is AB. So let's draw that segment. We have segment AB. Okay, and then we have another segment. We have another segment, segment BC. So BC. And in geometry, once again, if we are trying to show that two things are the same or congruent, we do like little markings right here. So that tells me that segment AB is congruent to segment BC. Now, let's think about this. If I have these two segments that are exactly the same, and it's telling me that B is the midpoint of BC, well, how can B be in between B and C when B is already an endpoint here? Okay, B is already an endpoint here. So remember, midpoint, this word midpoint means that you have a point in the middle of a line or a segment, or something that's directly in the middle that's cutting it in half. So right here, it shows that B is an endpoint to this segment, not a midpoint. So that's one example that we can show where we're showing a counter example of that not being true. Another example is that if I just draw a figure, so say if I draw a triangle and I label this triangle A, B, C, right? I can say that segment AB, this segment right here, is congruent to segment BC, this segment right here. I can state that AB is congruent to segment BC, however, B is not the midpoint of BC. As you can see right here, B connects to segment BC, and B also connects to segment AB. So B clearly cannot be the midpoint of segment BC. Okay, example 3. Here we're going to match the properties of equality to the statement it justifies. So some of these should be very familiar from last year in Algebra 1, and we're going to use some of these same properties in geometry in our proofs. So let's start out with the first one, addition property of equality. So if you remember, if you're solving an equation and you need to balance that equation and something's being subtracted to something else on one side of that equation, to balance it, we have to add it. So if I'm looking here, out of all the statements that I have from A to I, and I go through each one, I show here that if I wanted to add something to both sides, then I would go with E. E here. If x minus 14 equals 17, then x equals 31. Well, what did I have to do here? I had to add 14 to both sides. And if I added 14 to both sides, that gave me a 31. So E would be my addition property of equality. Let's look at the next one, subtraction property of equality. So remember, we're doing now, this is the opposite operation, the inverse. So if I'm seeing something that's being added, on one side of my equation, I need to eliminate it, then I would do the inverse. I would be subtracting that. So let's look at all of these statements that I have here and see which one would allow me to subtract something on both sides. So let's look at H. It says if x plus 3 equals 15, then x equals 12. Well, how did we get the 12? Well, we had to subtract that 3 on both sides. 15 minus 3 gives me 12. So H would be an example of my subtraction property of equality. Let's look at the next one, multiplication property of equality. So this is just once again looking at what equation or what statement here that we have that shows that I can multiply on both sides of my equation to balance it. So if I'm looking at all of them here, I see that we have F here. F. If y divided by 3 equals 12, then y equals 36. Well, what do we have to do to get y by itself? Well, I had to multiply by 3 on both sides. So if I take 12 times 3, well, 12 times 3 is 36, and if I multiply y over 3 by 3, my 3's cancel out and I'm left with y. So F is an example of the multiplication property of equality. All right, let's look at my next one, division property of equality. So that means I'm looking at a statement where I would have to divide. I would have to divide in order to eliminate or balance my equation. So let's look at G here. It says if 3x equals negative 45, then x equals negative 15. Well, if I wanted to eliminate this 3 to get the x by itself, I would have to divide both sides by 3. That would eliminate my 3, and I would have x equals, and then negative 45 divided by 3 would give me negative 15. So division property of equality would be statement G. All right, next one is distributive property of equality. So that means that I'm looking for a statement where I have a constant or some type of value on the outside of grouping symbols, and then I would have to move that constant or variable into my grouping symbols to distribute it. So if I look at my statements here, I can see that B here is an example of that. I have 3 as a constant outside of my grouping symbols, and I can use the distribution property to take that 3 and multiply it to everything that's inside of the parentheses, where I get 3 times A gives me 3A, and then 3 times B gives me 3B. So that's how I get this 3A plus 3B here. So number 5, distributive property, would be for statement B. All right, substitution property of equality. So with the substitution property of equality, I'm looking for something that I can plug in to make the statement true. Okay, I'm plugging something in to make a statement true. So if I'm looking at these statements here, I see that statement A here is a good example of the substitution property. It tells me if the measure of angle A equals 45 degrees, then 3 times the measure of angle A equals 135 degrees. So they told me that the measure of angle A is 45. So that means every time that I see the measure of angle A, I can just substitute it or plug it in. So here, if I plug in 45 here, for that value of the measure of angle A, I have 3 times 45, and 3 times 45 gives me 135 degrees. So A is a good example of the substitution property of equality. All right, let's look at the next one. We have the reflexive property of equality. So if I'm looking at the reflexive property of equality, think of looking at yourself in the mirror. It's not reflecting, it's reflexive. But you can think of it as mirroring itself. You have something equal on both sides of the equation, or you have 2 properties that are equal, or 2 values that are equal to each other. In geometry, sometimes we have 2 figures or 2 parts of figures that are equal to each other. And we'll see more of that when we get into proofs. And we call that the reflexive property. So looking at all the statements, I see that statement C here shows that I have 2 properties or 2 parts of some figure that are equal to each other. The measure of angle B is equal to the measure of angle B. Remember I talked about that reflecting. So think of this equal sign as a hidden mirror. Okay, think of it as a hidden mirror, and when angle B looks into the mirror, it sees itself back. So they see each other back in the mirror. So statement C would be an example of the reflexive property of equality. Let's look at the next one, symmetric property of equality. So the symmetric property of equality pretty much means that it's a reflection, okay? Something that's the same on both sides. So it's very similar to reflexive, but symmetric means that I'm looking at one thing and it's telling me it's that thing, and then I'm looking at that thing again and it's telling me it's the original property or piece or part it was from before. So if I look at these examples, I will be the best example of that. If BC equals RL, then RL equals the BC. That means that if A equals B, then B equals A. That means if I have a banana that equals an orange, then that orange equals the banana. It holds the same properties, it holds the same value. So I would be an example of the statement for the symmetric property of equality. Now all we're left with is the transitive property of equality, and that's D here. And that's pretty much stating that if I have two things that are equal and I have another set of two things that are equal, then I have the original part in one statement is now equal to one of the original parts in the second statement, based on something that they both have in common. So let's look at statement D. Statement D says X equals Y and then Y equals Z. So therefore X equals Z. So you have to first look at this first statement, which is X equal Y, and then Y equals Z. What do both statements have in common? Well, both statements have Y in common. Because both statements have Y in common, now I can say that now these two parts of those both statements are now equal. So transitive property is pretty much saying that if I have something that's equal in two different statements, then it makes two other parts of those two different statements equal as well. So then we can say that 9 goes with D, which is the transitive property of equality. Okay, so now we're on to number 4. It says use the proof template to write the statements and reasons for the proof in the correct order. So guys, we are now diving into what a proof looks like. So what you're looking at is what we call a 2-column proof. As you can see, there's 2 columns. There is a statements column, and then there's a reasons column. In this proof, we are given some information. The information that they give us is this equation here of 4 times the quantity of x plus y equals 48. And they tell us some other information that the value of y is equal to 6. And they want us to prove that x equals 6. So this is very similar to solving an equation, but now we're going to use the properties that we just had, the properties of equality in the previous example, to now show you how to solve this using a proof. So the very first thing we do in a 2-column proof is write the statement. So we have statement number 1 here, and statement number 1 was given in the problem. It's right here at the top. 4 times the quantity of x plus y equals 48. So because this was given, the reason in this problem or in this proof is going to be given. Okay, it's going to be given. We have the second statement here, so let's be consistent. That's the first statement. This is the first reason. So we have the second statement and the second reason. So the second statement here is y equals 6, which is also given. So since that statement is given, the reason is also given. All right, so now we have this third statement here. The third statement states we have 4 times the quantity of x plus 6 equals 48. Well, remember, our proof goes in sequence. So normally if you're trying to find the reason for one statement, you always try to look at the statements and reasons that were given before it. So it tells us here in statement number 2 that y equals 6. Now in statement number 3, it says here that x plus 6 here. So now something's missing, something happened. This used to be a y. So what property was used to replace the y now for the 6? Well, if we think back to example 3 in the properties of equality, I can say my third statement should be the substitution property of equality. If I substitute anything into a equation or statement, that is the substitution property of equality. Now let's look at statement number 4. So statement number 4 says 4x plus 24 equals 48. Well, once again, in proofs, we always look at the statement and reasons that came before it to help us determine what the next statement or reason is going to be. So your question should be, how did they go from statement 3 to now statement 4 with 4x plus 24 equals 48? Well, in this previous statement, it said that 4 was on the outside of grouping symbols. So that means I had to do some type of distributing to get my next statement. So that helps me right there for my reason to know that the reason is going to be the distributive property of equality, because now this 4 has been multiplied to everything inside of my grouping symbols. All right, let's look at statement 5. So statement 5 says 4x equals 24. Once again, we look at what happened in the previous statements and reasons. So the previous statement says 4x plus 24 equals 48. Sorry. So how do we get from 4x plus 24 equals 48 to 4x equals 24? Well, that means some type of property had to take place. So if we notice, I am using the subtraction property of equality. Let me clean that up. Sorry, guys. I'm going to use the subtraction property of equality to get rid of that 24. As you can see here, there's no 24 by this 4x on the left side of my equation. So that means I use the, not 4, 5. Statement 5 is the subtraction property of equality. Okay, now I'm going to my last statement, and my last statement says that I have x equals 6. So once again, we look at the previous statement that came before statement 6, and that's statement 5, where we have 4x equals 24. So the question is, how did I jump from 4x equals 24 to x equals 6? Well, once again, we had to use some type of property of equality. And I know that property of equality had to be division because I need to get rid of that x in order for x to be by itself or to be isolated. So here I used, sorry, that's supposed to be 6. I'm ahead of myself. 6 is the division property of equality. And as you can see, when you finish your proof will always finish out with what was proven. And as you can see, this is what we were trying to prove. We were trying to prove that x equals 6. And that's exactly what we did. We went through all of the steps in finding the reasons for the statements that were given, and we used specific properties to show that these statements and reasons were true. Okay guys, let's look at example 5. So it says use the diagram to complete the proof by filling in the blanks. It is given that AB, segment AB here, is equal to segment BC. So once again, if I'm shown that two segments are equal within a diagram, I'm going to mark up my figure with these what we call tick marks to show that these two segments are equal to each other. Then they want me to prove that AC, the full entire length of the segment, is equal to 2 times the length of segment AB. So let's start our proof here. We're asked to fill in 2 of the reasons within our proof. So statement number 1 says we have AB equal to BC. Well, that was already given to us and we've already marked it in our picture. Statement 2 says AC is equal to AB plus BC. So if we remember back from lesson 1 with the segment addition postulate, okay, that is the reason for this statement for these 2 segments to be added and equal to the full length of AC. The third statement says that segment AC is equal to segment AB plus AB. So let's think about this. Why would they replace segment AB with segment BC? Well, within a proof, we always look at the statements and reasons preceding it. So if we go back to statement 1, it told us in the given that segment AB is equal to segment BC. So if these two segments are equal, then they are the same. So that means I can replace BC with AB. And what reason would we give that? Well, that would be the substitution. Substitution property of equality. So that would be the reason why we can make the statement for number 3. And looking at statement 4, to finalize our proof, we have AC is equal to 2 times the length of AB. Well, we have 2 ABs here. In the previous statement, in statement 3, we have AB here and an AB here. If we combine those ABs, that means we have 2 of them, so I can rewrite it as 2 times the length of AB. So because I was able to rewrite that, that means that I am now using another property of equality, and that property of equality is called the distributive property of equality. I can distribute this to AB because there are 2 of them, and then we have to look to see if we actually proved what our proof was asking for, and yes, we did. We showed that twice the length of AB is AC. Okay guys, we're in our last example, example number 6, where it says to prove the linear pair theorem. So this is another proof that we're going to do, but now dealing with angles. So it says here that the given is angle MJK and angle MJL are linear pair of angles, And we want to prove that these 2 angles are supplementary. So let's just do some background information as far as the vocabulary that's being used in this problem. So what is a linear pair? So a linear pair is when we have 2 opposite rays of each other that create a straight line. So for example, we have ray JK here, and then we have ray JL. And these 2 are opposite rays, and these 2 rays create a straight line. Essentially, it creates a straight angle. We talked about straight angles equal 180 degrees. Now we want to prove that these 2 angles MJK, so that's this angle right here, MJK, is supplementary to angle MJL, and that's this angle right here. So that means we want to prove that these 2 angles actually form 180 degrees. So to complete this proof, we're going to write in the missing reasons, and then we're going to use the reasons here from this little bank that I have. So these are 3 or 4 different reasons, and we're going to make sure that we plug them in the right spot. So let's start with statement number 1. Angle MJK and MJL are a linear pair. Well, we know that already to be true because that was given to us in the problem. It says here that the next statement number 2 says ray JL and ray JK are opposite angles. Well, I just defined for you what opposite angles create, and those opposite angles create linear pairs. So we can use, well, we already used given. So now we can use the definition of linear pairs. So this would be the definition of linear pairs. Okay, so we got that one out the way. And now number 3 says ray JL and ray JK form straight lines. So we just stated that when you have linear pairs, the opposite rays form straight lines, so that is true. And we know that the reason being the definition of opposite rays for the reason number 3. And then we can go in to say that for statement number 4, the angle measure for LJK equals 180 degrees. So that would be this angle right here, LJK. I know that this angle is a straight angle because it's created by 2 opposite rays, and those 2 opposite rays are linear pairs. So I can say that it is a straight angle because it is 180 degrees. So we have that reason here. Now let's look at statement number 5. Statement number 5 says the measure of angle MJK plus the measure of angle MJL equals the measure of angle LJK. So once again, MJL is this angle here. MJL, I'm sorry, that was MJK, that was that angle, and then MJL is this angle right here. And it's telling me this statement equals the full length of the straight angle LJK. So remembering back to lesson number 2, we talked about if I have a piece of one angle added to a piece of another angle to add up and equal a full angle, that is called the angle addition postulate. Okay, so that would be the reason for number 5. So we can get rid of that one now. So now we're just left with the substitution property of equality, but we're going to go over that so we can make sure that this proof makes sense. So looking at statement number 6, we have the measure of angle MJK plus the measure of angle MJL equals 180 degrees. Well, why are we going to use the substitution property of equality? Well, remember, we always go in the proof back to the preceding statements and reasons to help us find the reasons and statements of the ones that we're looking for. So remember, the measure of angle LJK, that was a straight angle, right? We saw that here in reason number 4. And we know that it's a straight angle because it has two opposite rays that form a straight line. And if we have a straight line, we know it equals 180 degrees. So that means I can replace or substitute the measure of LJK with 180 degrees. So that would be the substitution property of equality. Okay, and now we can finish off our proof with the last statement, number 7, that the measure of angle MJK and the measure of MJL are supplementary. Remember that word supplementary means the sum of two angles whose measure is 180 degrees. We can actually say that these two angles right here, let me highlight them, these two angles right here, in fact, are supplementary because they are forming a straight line. And the reason for that is the definition of supplementary angles. Okay guys, so if you haven't done so already, please make sure that you're completing your warm-up activity in your OneNote class folder in Microsoft Teams. That is in lesson 3 in topic 1. And of course, like always, I will be reviewing all of these problems that I went through in the video during our virtual class session. Good day guys, and I hope to see you soon.